All right, so I want to talk about how to solve a system of equations by graphing. So first of all, let's talk about what a system of equations is. A system of equations is just when you have multiple equations here. So I have a couple equations here, this green one and this orange one. We call it a system when there's more than one. So you've got an equation here, you've got an equation here. We'd like to get both of them to be true at the same time. So there's in this case, there's one specific pair of values of x and y that if you plug them in, they'll make both of them true at the same time. We're just trying to figure out what those are. So let's go ahead and graph the first one. So I'm going to take the green one here and graph it. And generally what I recommend and why we're starting off with an easy one is get the y by itself, which is true in both cases. This right here is the y-intercept. This is where this line is going to cross the y-axis. If you think about if x is 0, so right here is the y-axis. This is where x is 0. So what we're going to do is if x is 0, then this part essentially goes away because 1/2 of 0 is 0. And you're left with when x is 0, y has to be 2. So what we'll do is we'll come over and when x is 0, y is 2, we'll put a point right there on the graph. And now what we're going to do is just look at the slope of this line. So this is the y-intercept. This is the slope. Some of you may remember y equals mx plus b. This is the m. This is the slope right here. This means that we're going to go up 1 over 2. And this is specifically up 1 right 2. So when I go over, I'm going right 2. So I'm going to go, you can imagine from this point here going up 1 and then over 2. So we're going to put a point right there. And we're just going to keep doing that. So if we go up 1 over 2, up 1 over 2, up 1 over 2, up 1 over 2, so on and so forth. Then you can also go, if you go up 1 right 2, you can also go down 1 left 2. And that'll still continue to draw our line. Okay, that should be plenty of points there. And what you'll want to do is go ahead and connect this line. So we'll go ahead and draw a nice straight line through all those points. So that is the equation of our first line. We have graphed that. Now what we're going to do is we're going to come over to the orange line and do the same thing. So the y-intercept, we're going to start at 9 and then we're going to go down 3. There's no over here, but you can imagine any number, if you put it over 1, is still equal to itself. So we'll come up to positive 9, drop a point there, and now we're going to go down 3, right 1. So down 3, right 1, down 3, right 1. Hey, there's our solution. Down 3, right 1, down 3, right 1. And we'll go ahead and draw a nice straight line through that. And so the goal here when you solve a system of equations by graphing is to find the place where the two lines intersect each other. And I think that's pretty easy to see here that the solution in this case is right at this blue point, which happens to be at 2, 3. What you should do here is you should check 2, 3 and plug it back into both equations. So we'll take the first equation here and we'll say the y value is 3. So is it true that 3 is equal to 1/2 of, and the x value is 2, plus 2. So all I did was take this equation and I plugged in the y value, which should be 3, and the x value, which should be 2 from this point. So is that true? Is that true that 3 is actually equal to 1/2 of 2 plus 2? Yeah, that's correct. What about this one? Is it true that 3 is equal to negative 3 times x, which is 2, plus 9? So is that true? 3 is equal to negative 6 plus 9. That is also true. So this is a really nice way to check and make sure that your solution is actually correct. So let's look at a couple more examples here. How about this example here? So solve the system by graphing. So we've got y plus 2x is equal to 7, and we've got 2y minus x is equal to negative 1. So like I said on the last problem we did, what I recommend is getting the y value by itself. This is called, when you do that, it's called slope-intercept form, and it just makes it really easy to graph. So on this first one, I'm going to subtract 2x from both sides. And we're going to finish with, and I'll put this in blue here, we're going to finish with y is equal to, you could put 7 minus 2x, but I like to put that x part first, just because I'm so used to that slope-intercept form. Hopefully you guys remember y equals mx plus b. This is called slope-intercept form here, and it's really nice because the m happens to be the slope and the b happens to be the y-intercept. It's just super convenient, quick, easy way to graph something. So let's graph this. So we're going to start at positive 7, and then we're going to go down to, and there's no over here, so we just kind of assume that that's 1. So if we go up to 7, and then we go down to right 1, down to right 1, down to right 1, down to right 1, so on and so forth. You can also go up to left 1, up to left 1. That's going to be our line there. Let's go ahead and draw a line through it. So there's our first line. And now let's do our second line. So the red guy over here. So we want to get the y by itself. So I'm going to add x to both sides. And when we do that, we get 2y is equal to, let's say x minus 1 here. And then now we're going to divide both sides by 2. And actually, instead of dividing that right side by 2, I'm going to divide each part of this by 2, because that's what really happens when you do this. So we're going to be left with, over here, those 2's will cancel, so we'll be left with y is equal to, basically, x over 2 minus 1/2. I'm going to actually write x over 2 as 1/2 x, because they are the exact same thing. So this right here is nice slope-intercept form. And let's go ahead and graph this. So, and this one is a little ugly. So it's going to start at negative 1/2. And then we're going to go up 1 over 2, because that's the slope there. So let's do it. We're going to go up 1 over 2, up 1 over 2, up 1 over 2, up 1 over 2, and then you can go down 1, left 2, down 1, left 2, down 1, left 2, so on and so forth. Let's get a nice ruler here and draw a straight line through that. So here's our second line. And when we look to see where those two lines cross, it looks pretty clear to me that it's right here at this point. So if you wanted, you could check if that point right there happens to be 3, 1. So that would be our solution. So our solution would be 3, 1. Some people might say x equals 3, y equals 1. Same thing. And if you go through and check both of those through the original equations, so if you plug in 1 for y and 3 for x here, they would both work. If you plug in 1 for y here and 3 for x, that would work as well. Okay, so one last example. So solve the system by graphing. So first order of business is to get y by itself. I would probably subtract x here. So you get negative y is equal to, I'm going to say negative x plus 2. And what I would do here is I would actually divide by negative 1. And I would divide everything over here by negative 1 as well. When you do that, you'll get, let's actually put this in green now. You should get y is equal to, the negatives will cancel there. Let's see. Okay, so basically we've got negative x divided by negative 1. That's just x. And then you've got plus 2 over negative 1. That's just minus 2. Another way you can rewrite this is 1 over 1x minus 2. I really like to have that slope there. All right, so that's the first one. Let's do the blue one now. So we're going to get y by itself. I would probably subtract 8 here from both sides. And so we'll get negative 2x minus 8 is equal to 2y. And then let's divide both sides by 2 here. So everything's going to get divided by 2 there on that left side. So this is going to be negative x minus 4 on the left, and then the 2's will cancel, so you'll just be left with y on the right. I'm going to switch this around, so y is equal to negative x minus 4. I just like to have the y on the left. And then, again, so we don't really have a slope with that x there. It just says negative, so we can consider that negative 1 over 1x minus 4. And let's actually put that in blue. Okay, so let's go ahead and graph these. So the green one, we're going to start at negative 2, and we're going to go up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. We can also go down 1, left 1, down 1, left 1, down 1, left 1. And we'll go ahead and draw a nice straight line here. So here's our first line. Now let's go ahead and plot the points for our second line. So we're going to start at negative 4. And we're going to go down 1, right 1, down 1, right 1. So down 1, right 1, down 1, right 1, down 1, right 1, down 1, right 1, up 1, left 1. Oh, looks like that's the solution right there. Up 1, left 1, up 1, left 1. You don't really need that many points. I just like to put them in there. It makes drawing it a little easier. And we'll go ahead and draw this in here. So our solution then to this problem is right where these guys intersect, and that's going to be at negative 1, negative 3. So if you went and plugged that in, if you plugged in negative 1 for x, and you plugged in negative 3 for y, it would work for both of the original equations. All right, so we got a couple weird cases to talk about. And the first one is right here. So let's actually just solve this out. Let's actually just graph the orange one because it's already in slope-intercept form. So y is equal to 1/3 x plus 3. We'll go ahead and put that y-intercept up there at 3. And then we're going to go up 1, right 3. Up 1, right 3. Up 1, right 3. Up 1, right 3. Down 1, left 3. Down 1, left 3. Down 1, left 3. Go ahead and draw the line there on that one. Okay, so here's our line. And now let's go ahead and solve this green equation here for y. So we're going to divide everything here by 6. And we will end up with y is equal to 2/6 x plus, and then 6 over 6 is just 1. Okay. So if you'd like, you can graph it as is. Sometimes I like to simplify the fraction here. 2/6 is really 1/3. You can divide the top and bottom by 3. So, all right, so the green one is really actually 1/3 x plus 1. So let's do that. So we'll go to plus 1, and then we'll go up 1, right 3, up 1, right 3, up 1, right 3, down 1, left 3, down 1, left 3, down 1, left 3. And we'll draw the line. Here's our line. And so hopefully you're starting to notice what's weird about this one is that these will actually never intersect. And the reason I know they'll never intersect is because part of the reason that other lines intersect is their slopes are different. And so eventually the lines will cross, but these start at different points and their slopes are the same. So you can imagine running a race and you're both going up 1 over 3, up 1 over 3, up 1 over 3, up 1 over 3. It's not like one of these lines is ever going to overtake the other line. It's never going to go higher than the other one. So these will never intersect. So this is one of the weird cases where there are no solutions here. So if your lines never intersect, you have no solutions. And that's true if you actually try to find a number for x and y that works in both of these equations at the same time, you will never be able to find one. All right, so our last system of equations, which is another bizarre example, is this one. So we've got y is equal to 2x minus 3. Let's go ahead and just graph that one. So we'll start at negative 3, and we're going to go up 2 over 1. So up 2 over 1, up 2 over 1, up 2 over 1, down 2 left 1, down 2 left 1, down 2 left 1. And we'll go ahead and draw the line. So here's our line. And now what we're going to do is the blue one. So let's go ahead and solve for y here. I would add 4x to both sides if we're trying to get the y by itself. So we've got 2y is equal to, let's say 4x minus 6. You could write negative 6 plus 4x, but I like to have that x first. And then we will divide by 2 here. Everything gets divided by 2. And we're going to finish with y is equal to, so 4x over 2 is just 2x. And then negative 6 over 2 is just minus 3. Okay? And so let's graph this blue line now. So we're going to start at negative 3, and we're going to go up 2 over 1. And so, well, this is kind of weird. If you look at it, this is actually the exact same line that we had before. So when you draw the blue line, we'll go ahead and do that. When you draw this blue line, it is literally on top of the red line. So what does that mean? That means that there are an infinite number of solutions. So we'll go ahead and write that. So we have an infinite number of solutions. So anytime you have two lines right on top of each other, you have an infinite number of solutions. Now, just for clarification, this is not to say that every possible combination of x and y works as a solution to this system of equations. Like, for example, if you put in 1 for x and 10 for y, that would not be a solution. What it's saying here is that if you look around, you'll be able to find an infinite number of solutions for x and y. Let me point out a few of them to you. If you plug in 2 for x and 1 for y, that's a solution. If you plug in 3 for x and 3 for y, that's a solution for both systems. Or sorry, for both equations. If you plug in 4 for x and 5 for y, that would work for both equations. Normally, typically when you work on a system of equations, you're usually going to have one solution. There's one place where the lines cross that works for both equations. But this is a weird case where there's actually, technically, you could go on forever, right? You could, if you just look at the line here with me, you could find all of these solutions and they would go on forever, even past where this line is. And so you would have an infinite number of solutions.